Bipolar covalent bonds using the electronegativity values in a periodic table. So when we started the course, we talked about either having ionic compounds or molecular compounds, and that had to do with whether electrons were transferred from one atom to another, as we saw with ionic compounds like sodium chloride, where the chloride would take a negative charge, and it would get that negative charge by taking an electron from the sodium, so the electrons were transferred. When we talked about covalent compounds, we talked about sharing bonds, and in Lewis structures, we represented these shared electrons as lines drawn between the central atoms. Now, one of the interesting things that happens is electrons are not always shared evenly. So if we look at oxygen, there's relatively an even distribution of electrons between the two oxygen atoms. But if we go down to a carbon-oxygen bond, there will be less electron density around the carbon and more around the oxygen. So this oxygen will take on a partial negative charge. It's not the magnitude of the chlorine, not that much. It's only taking part of the charge, and the carbon in this case will be electropositive. It will have a partial positive charge. And this bond is what we would call polar. So the polarity is the separation of charge. It's not as complete as we saw in ionic compounds, but it's greater than you see in a nonpolar covalent bond. So we'll call this nonpolar covalent. And we'll label this alternative option here, this one where there's some skewing but not a total transfer, as a polar covalent bond. So essentially we're taking the division earlier in the course of molecular compounds and ionic compounds, and we're sort of adding a third option on this scale. Now, we're going to, in a sec, talk about differences in electronegativity, and from 0 to 0.39, we're going to label it as nonpolar covalent. From 0.4 up to 1.99, we'll label it as polar covalent. And then 2.00 and up, we'll label as ionic compounds. These electronegativity values are theoretical values that describe how strongly atoms pull on electrons. And if they pull with similar magnitude, then the difference, the delta, En, difference in electronegativity, will be close to 0. But if one atom pulls the electrons more strongly than another, we'll get this distortion. In this example here, oxygen is more electronegative, has a higher electronegativity value, pulls the electrons more strongly, and so there's greater electron density around the oxygen. But at some point, that difference gets so large that you effectively see transfer of electrons. You're going to get these electronegativity values off of a table somewhere. It might be in your book, it might be on an exam handout, but on our exam handout, it's this bottom number here. So fluorine has the highest electronegativity in the periodic table at 3.98. All the way in the other corner, the bottom left corner, is francium with 0.7. And so fluorine pulls most strongly on electrons, shared electrons and bonds, and metals tend to not pull strongly at all. So when we combine metals and nonmetals, that was our rule for ionic compounds. Nonmetals tend to have high electronegativities. Metals tend to have low, and so we end up with that large separation of charge. So let's try a couple. So we can look at a carbon-hydrogen bond, and when we're looking at bond polarity and using electronegativities, you look just at the two atoms in a bond. You consider one bond at a time. So a carbon and a hydrogen, and you'd go to the periodic table and you'd look them up, and the carbon is 2.55, and the hydrogen is 2.20. You're always going to subtract the smaller number from the larger number. So the 2.55, and then subtract the smaller number, 2.20, means that my difference in electronegativity here is 0.35. The general cutoff that we'll use is 0 to just under 0.4 is going to be nonpolar covalent. So this is nonpolar covalent. Now, just a word of caution, different people may use different cutoffs. So if you're doing the online homework system, it might have a slightly different cutoff than your book. So read the instructions and the descriptions to problems to make sure you're using the correct cutoffs. If something's nonpolar covalent, we don't need to specify or describe how that charge is separated, so we're done. When we go to this next one, when we look at the chlorine has an electronegativity of 3.16. I'm just getting this number out of that periodic table. And aluminum has 1.61. So I take the larger, 3.16, minus the smaller, 1.61. And I get a difference in electronegativity, in this case of 1.55. That falls in that range of 0.4 to just under 2 for polar covalent bonds. Okay, and so this is an intermediate range where we have some separation of charge, but not complete separation or complete transfer of an electron. And it's useful to know which atom is more electronegative or electropositive. The one with the higher electronegativity will be electronegative, and the one with the lower electronegativity will be electropositive. And so we could use these lowercase Greek letter deltas, but a common way to do this for polar covalent bonds is instead to draw a polarity arrow, and it's an arrow next to the bond pointing towards the more electronegative atom, towards the negative charge, and it has this little bar across on the electropositive end. To me, it sort of looks like a little plus symbol. Okay, but you would not draw it on top of the bond. That means something different. You draw it next to the bond, and that indicates that this is a polar covalent bond and points towards the electronegative atom. If we go down to the nitrogen in this case, this is 3.04. The oxygen is 3.44. Larger number minus the smaller number. This one comes out to be 0.40, and that's right on the cutoff. So the cutoff I'm using in this video was exactly 0.4 up to just under 2. This would be a polar covalent bond. Now, it's not as polar as the aluminum-chlorine bond, but it still is polar. And in this case, the more electronegative atom is the oxygen. That's the higher electronegativity value. It's going to have a partial negative charge. The nitrogen will have a partial positive charge. Now, if we look at fluorine and calcium, fluorine would have a electronegativity value of 3.98. That's the highest in the periodic table. And calcium has a value of 1.00. Okay, so we take the 3.98 minus the 1.00. And in this case, we get 2.98 as our difference, which is well into the ionic range. And it would be proper not to draw that bond, to give the fluorine a full negative charge, and the calcium, it will end up with a 2 positive, but it's going to have a second fluorine. It's only getting 1 positive charge from that fluorine, 1 electron that it gave up and was taken by that fluorine. And that's basically the process. Identify the electronegativity values of each atom, do a subtraction, and compare that delta En, or difference in electronegativity, to those cutoff marks for your problems. There are some complications that can show up. And so if we look at 2 oxygen atoms, those should each be the 3.44. So this should be 3.44 minus 3.44. So it should come out to be 0. So a nonpolar covalent. And the carbon-oxygen bond, regardless of whether it's a single, double, or triple, should be that 3.44 for the oxygen minus the 2.55 for the carbon, or 0.89. And it should be polar covalent. With the oxygen being more electronegative. Now, these last 2 examples are problems that show some of the limitations of this. And if we look at carbon monoxide, there is not significant electronegativity or partial negative charge on that oxygen. And that's because when we look at the Lewis structure assigns a positive formal charge to that oxygen and a negative formal charge to that carbon. Now the electronegativity of oxygen will shift the electrons in those pi bonds, in that triple bond, towards the oxygen and minimize that difference to some extent. But the structure of the molecule, the formal charge, what it needed to do to get the octets, can skew the polarity that we would get just by comparing electronegativity values. Similarly, if we look at ozone is all oxygen, so looking at these electronegativity values, there shouldn't be any charge separation, but we see it, and that's again when we look at formal charge. That central oxygen atom does not have enough electrons. It has a formal positive charge, and depending on which resonance structure we're looking at, those terminal oxygen atoms have negative charge. Now remember, resonance structures weren't accurate representations of the molecule. They were sort of two different views, and the reality is somewhere in the middle. I might draw it a little differently here, with partial bonds represented by those dashed lines and the lone pair up there. This oxygen atom has a positive charge. These two oxygen atoms share a partial negative charge. Okay, so ozone ends up being a polar molecule. It has polar bonds, even though the differences in electronegativity don't predict that. So the limitation on using this electronegativity difference to predict bond polarity is that it works when there's no formal overall formal charges in the molecule in the Lewis structure that you're working from.